we will be doing sample problems from section 3.3. So the first one we see here, we will be using the power rule. So what is the power rule? A quick review. If you have a function, x to the n, the power rule says you can bring that n out in front and then subtract 1 from that power. So the derivative would be n x to the n minus 1. Now, a couple things to point out for this rule. You have to have that variable here raised to the power of n. Now, they tell you that n must be an integer. In the future, we'll learn it doesn't have to be an integer, but that is what they tell you. I will give you some leeway and allow you to use it with fractions also, but that's what's going on. So in this first one, we see that t is our variable. That's t to a power, so we can apply the power rule here. So this will be f prime of t is 11 t to the 10th. So we brought the 11 out in front, subtracted 1 from the 11 to get the 10. All right? Number 10, it's tricky. So notice a couple of things. Our variable, in this case, is x. That is not x. Therefore, this power rule here does not apply. In fact, you should know that e is a constant. It's approximately 2.714. So essentially, this function is actually a constant. So 2.714 squared, or cubed, is approximately 19.9. So let me see, approximately 19.9. And you should know the derivative of a constant is always 0. It's a horizontal line. I didn't mean to do that. So at any point x, the derivative will always be 0. So that one's a tricky one. You have to understand the power rule, how it works. E is not your variable. Now in this one, we are fortunate that's our variable v. It is our variable raised to a power, so we can apply the power rule. The derivative of f with respect to v is 100v to the 99th. And remember, the 100 comes in front, just like we did here. Subtract 1 from the 100 to get our 99. What's going on in this next section? This section is the constant multiple rule. So what did this say? If you had a function, we'll call it h of x, and that's a constant times a function f of x, and you want the derivative of the whole thing, well, you learned you can pull the constant out in front and then take the derivative of the function separately and then multiply it to your constant. So that's what we need to do. I know in time you're going to do shortcuts, but you need to understand you have to follow these properties. It's dangerous to just make up your own rules and use them. So here we have a constant. We want the derivative. So the derivative of g with respect to w, w's our variable again, w's our variable, make sure that matches. We can pull the constant out in front. Wow, that's beautiful, isn't it? Oh, undo that. That was bad. Let me do this. Yeah, that was bad. So 5, 6 is our constant. Then we take the derivative of what's left. Now for the what's left, we use the power rule. So the 12 comes out in front, and we subtract 1 from the 12, we get the 11th. If we simplify that, we get 10w to the 11th. Now, some of you might be saying, I didn't have to pull that out in front. Can't I just bring the 12 and multiply it by 5, 6 and decrease that by 1? Yes, you can, but the reason you can is because the constant multiple rule. If I have a constant, I can pull it out, take the derivative, and now these get multiplied. I know in the future you'll probably go directly from here to here. You won't pull it out in front, but you have to understand why that works and what you're doing. So number 18, we have the same situation. We have a constant. And that constant is 1/4 being multiplied by our function, radical s. And s is our variable, and that's an s. So all we need to do is say the derivative with respect to s is the constant times the derivative of your function. Now, from the previous section, hopefully you remember the derivative of radical x is 1 over 2 radical x. So eventually what's going to happen is you're going to just know the derivative of that. You're going to do it so many times. It's 1 over 2 radical s. So I'm going to put that there, and we found that in the last section we did, or actually the definition of the derivative is when we did that. But you may say, can't we use the power rule? So technically, no, because the power rule only works for integer, but I will let you because we're going to get there. So if you have the function f of x equals x to the 1/2, and you want the derivative, right now, you're not supposed to do with fractions. That's going to be a future theorem. It's supposed to be whole numbers, but you'll see it works. If you pull the 1/2 out in front and decrease that by 1, you will get 1/2 x. Decrease this by 1, you get negative 1/2. To make that negative exponent positive, you have to move it to the bottom. It becomes x to the 1/2, and then you get that answer. So that's what we got here for the derivative of radical s. All right, so that's the second property, constant multiple. The next one is going to be this. Suppose you have a function h of x that consists of two functions, f of x and g of x, and you want the derivative of h of x. Well, this property says you're allowed to take the derivative of the first function and then take the derivative of the second function and then add after. So that's the sum and difference properties. So using that, g prime of x will be the derivative with respect to x of 6x to the 5th minus the derivative with respect to x of x. Now the final steps here. Technically the 6 would have to come out in front. So you would get 6 and then use the power rule. The 5 comes out in front of the x, and you decrease that 5 by 1, you get 4. And then you don't see it, but there is an exponent right there. It's 1. So we bring the 1 in front and decrease that by 1, and we would end up with 1x to the 0 power. And this simplifies to 30x to the 4th, and x to the 0 is 1, so we're just going to get minus 1. And that's using the sum and difference identities, or sum and difference theorem. And here, just going a little faster because I think you're getting the hang of it, 4, we talked about the derivative of a radical. That's going to be 1 over 2 radical t minus 1/4. The derivative of t to the 4th is 4t cubed using the power rule. And the derivative of t to the 1st is going to be 1t to the 0. And the derivative constant 0. So this becomes 2 over radical t minus t cubed plus 1. Bammo. So that's combining the sum and difference theorem, the constant multiple theorem, and the power rule. All right, here is where the danger comes. You might do, oh, I know this. I want the derivative. I just take the derivative of this, which is 3x squared. The derivative of 3x squared is 6x, and the derivative of 1 is 0, and bam, I have my answer. And you would be extremely wrong. That is muy bado. Because you were never told how to take the derivative of a product. You have not had a rule that teaches you that. And to assume you just take the derivative of each would be very bad. You did have a rule about two things being added. You take the derivative of each individually and just combine them. You never had a rule for a product, so don't assume that there's a rule. So you actually in our next lesson will learn how to do a product and a quotient, but that's the next lesson. You do not know that yet. So you need to rewrite this to where there is not a product. So we're going to distribute that and rewrite h of x. So in your homework, when you encounter this, you will do it this way. 3x to the fifth plus x cubed. Now you can take the derivative. You bring the 5 in front, decrease the 5 to a 4. You bring the 3 in the front and decrease the 3 to a 2, which can be simplified to 15x to the fourth plus 3x squared. That's the derivative of h of x. Now, the same thing here. Don't think you can take the derivative of that and the derivative of that and be done. You have not been told that's how you take the derivative of a quotient. You will learn that in the next section. So this one, we actually need to rewrite this. On the top, there's a common factor of x to all three. So I take that common factor out and I'm left with this. On the bottom, there's a common factor of x. So I'm going to take that out and I'm left with that. Now the next step, I'm going to rewrite h of x one more time. This is factorable. That factors to x minus 4, x minus 2, and on the bottom we have that. And you will now be excited because the x minus 2's cancel and the x's cancel. And so we are left with just this. H of x is just x minus 4, but I want to point something out. When x is 0 and when x is 2, the denominator is 0. And when the denominator is 0, you produce either a vertical asymptote or a hole. But since they canceled, we actually have holes or removable discontinuities at 0 and 2. Therefore, this function does not exist at 0 and 2. I want to point that out. There are holes there. So when you take the derivative, what's the derivative of that, which is 1, and the derivative of that is 0. So my derivative is 1, except the derivative does not exist at 0 and 2. Why? Because there were discontinuities there, and we know if a function is not continuous, the derivative does not exist. Bam. Let's keep going. A few more examples. Equation of a tangent line. You should think this is the equation of a line if I know two things, the slope and a point it goes through. Well, they're telling me a point it goes through is 0. That's my x1. How do I find y1? I plug my x coordinate into the function to get the y coordinate. So it's going to be y of 0, which is e to the 0 over 4 minus 0. But e to the 0 is 1. So y1 is 1/4. x1 is 0. The next question is, I have that and that. How do I find the slope? And you should know the slope is given by the derivative of the function at the point of tangency. So what is the derivative? Well, the 1 over 4 is a constant, so I pull the 1 over 4 out. And the derivative of e to the x, that's one of the theorems we had. It's e to the x. It's itself. And this, there's a 1 there, so it's 1x to the 0. So this derivative would be 1/4 e. We're plugging in 0 in for x, so that's going to be 0 minus 1. E to the 0 is 1. 1/4 minus 1 is negative 3/4. Let's plug everything in. We get a 0 for that, a 1/4 for that one, and the slope will be negative 3/4. Y minus 1/4 equals negative 3/4 x minus 0. Bam! Equation of tangent line. Lesson, the derivative of e to the x is itself. Let's keep going. They want to know when the slope of the curve is 0. What tells us the slope of the curve? Rightio, the derivative. The derivative will be 3t squared minus 27. And they want to know for part A, when will the slope of the curve be 0? The derivative of the slope of the curve. So basically you're saying when is the derivative equal to 0? I add 27 to both sides. I divide both sides by 3. I get 9. When I square root, I get plus or minus square root 9. So plus or minus 3 is the answer for that. For part B, I want the derivative or the slope of the tangent line, or what they call the slope of the curve, to be 21. That's the slope, so I set the derivative equal to 21. What does that give me? I'm going to add 27 to both sides, gives me 48. I'm going to divide both sides by 3, and that's going to give me 16. I square root both sides, I get plus or minus square root of 16, plus or minus 4, bam. That is, or those are the 2 points where the slope of the curve is 21. Let's keep going. What does that mean? Horizontal tangent line. That means the slope is 0. A horizontal line has a slope of 0. So what is the slope of the tangent line? Hey, that's the derivative, which is 2e to the x minus 6. It's the derivative of that. So part A, when does that equal 0? I add 6 to both sides. Divide both sides by 2. How do I get rid of e? You should know ln is the inverse function of e. So I ln both sides. Those cancel. And I end up with x equals ln of 3. Bammo. Part B, now I want it equal to 12. Well, same thing. I take my derivative, and I set it equal to 12. Add 6 to both sides. I get 18. Divide both sides by 2. I get 9. I ln both sides. See how easy this is? You should know ln cancels out e to the x. X is ln 9. Beautiful. Let's keep going. All right, we are told big F is f plus g. So take the big derivative of f. I was told earlier that that's going to be the little derivative of f plus the little derivative of g. Okay, can we do that? Well, here's f right here, and here's 2. What's the derivative of f at 2? Well, it's the slope of the tangent line, but the slope of that line is negative 3 over 1, so simply that's negative 3. G prime of 2 is the slope of the tangent line at 2, so g is 2 right there. What's the slope right there? That looks like a slope of 1 to me. So that's going to be 1, so the answer is negative 2. Bingo, bango. Let's do the next one. F prime of 5, well, big F is little f plus little g. So it's going to be the derivative of little f at 5 plus the derivative of g at 5. We can do that. This is pretty easy. 5's right there. F's right there. What's the derivative right there? It's the slope of that line, which is 1. And g is right there. What's the slope of that line? Negative 1. Plus negative 1. That is 0. And I added a bonus, g of 5. But g is 3f plus g. 3f plus g. 3f plus g. That's going to be, so the derivative of that will be 3 f derivative at 5 plus the derivative of g at 5. Well, what's the derivative of f at 5? We already did that. That's 1. And the derivative of g at 5, we did that last problem. That's negative 1. So sweet. 3 plus negative 1, that answers 2. Using properties, so we're using the sum and difference properties for derivatives and the constant multiple rule. You just pull that constant out in front. All right, last one, bonus. How do you do this? I plug 0 there and 0 there. I get 1 plus 1, which is 2, minus 2, which is 0. It's 0 over 0. Do I factor and cancel? Do I multiply by the conjugate? What do I do? Okay, here is the craziness. You have to recognize this is the definition of the derivative, and it's of this form. This form. So what looks familiar? There's h, there's h. Oh, x plus h, or excuse me, let me do that over again. X plus h, wait, there's my x plus h, there's my x plus h. So my x is 1. So what's happening, this is f prime of x, this is finding the derivative at 1. So I'm going to change this. F prime of 1 is now the limit as h approaches 0 of f of 1 plus h minus f of x over h. Now looking at this 1 plus h, it's there and there. This is the tricky part. You have to recognize the function. F of x is going to be x to the 8th plus x cubed. Let's see if this makes sense. If I plug 1 plus h in there and there, what do I get? Well, amazingly, I get that. All of that is f of 1 plus h. Okay. Now I have minus f of x. I messed up there because our point is 1. So that should be a 1 there. So let me replace that. Is f of 1 there? What's f of 1? That's 1 to the 8th plus 1 to the 3rd. That's 2. But look, 2. That's 2, and that's 2. So we look at this, and we recognize this ugly thing is the derivative of the function at 1. So what is f prime at 1? Well, I can find f prime of x. Let's use our derivative rules of that. I bring the 8 in front, decrease the 8 to a 7. I bring the 3 in front, decrease the x to a 2. Now I plug in 1, and I get 8 times 1 to the 7th plus 3 times 1 squared, and that gives me 11. That is the answer to this limit, because I recognize this is a derivative, and instead of figuring out that limit, I realize it's actually the derivative of f. I find the derivative of f, and I plug in my 0.1. Craziness. That's why you need to understand the derivative formula. That's all, folks. Goodbye.